then we'll go for lunch. So without much further ado, we just begin with Tasif, right? And Fadina.
Yes.
Yeah, so just introduce yourself and then start your talk.
Hello everyone. Today I'll be presenting our paper that is equivalent encoding based of variational autoencoder for coding tertiary structure generation with my co-author Fadina. Now, as we I think you probably know that it's a pretty complex task to just visualize the structure space of a protein tertiary of a protein molecule. So here is a simple approach that we have adopted that for this paper. Now, at first, due to short presentation time, I'll be skipping over some of the basics, and I'll be moving on to the details of rigorous matrix, that is the matrix that we have used for evaluating our generated structures. Now, at first, we have the backbone-based matrix. Now, in a protein structure, the backbone places consecutive C-alpha pairs as at a distance of 4 angstroms. Sorry,
the slides are not sharing.
sorry for the interruption. Yeah. So at first we have the backbone-based matrix. Now, in a protein structure, the backbone places consecutive C-alpha pairs at a distance of almost 4 angstroms. Now, to get the backbone score from a particular protein fragment, what we can do is we can simply compute the equidistant distance between consecutive C-alpha atom pairs, and then we can have the total number of C-alpha atoms that are within 4 angstroms of each other. So the expected score here is k-1 for a fragment length of k. Now, although this task is trivial, it can reveal a lot about the quality of the model and the generated conformations. Then we have the short-range contact-based matrix, for which we look for contacts or atoms that are placed within no more than 4 positions away from each other along the sequence. And then we have the long-range contact-based matrix, for which we look for atoms that are placed further in the along the sequence. Yeah, so now moving on to the goal of this work, we have a twofold goal of this work. The first one is that we are proposing a novel end-to-end generative model framework that is a new formulation under equivalent graph neural networks based encoding and graph variational autoencoder. So the first question that might arise is that why do we need end-to-end models? The reason is that we are tracing to names and corresponding coordinates as inputs and output as well. So we don't want to rely on any intermediate contact only generation, for which we can from which we would have to resort to some sort of complex methods to recover our generated coordinates. Then we have proposed a novel loss function through which we can control properties such as the number of backbone, short-range contacts, and long-range contacts. And these are the metrics that we have sort of discussed in the previous slide. Now, moving on to the architecture of our model. Here we have the architecture that is essentially a graph variational autoencoder. Now, as an input, we are taking 3D coordinates, its corresponding residue types, and its corresponding contact maps. Now, this is being fed into an encoder which can be thought of as 1 or more layers of equivalent graph convolutional layers or ETCL layers. Now, in ETCL layer, at first we have the coordinate to radial model, which gives us the relative square distance between 2 coordinate embeddings. Then we have the edge model, as you can see here. So this basically this one here, where the output of the coordinate to radial model is given as input, and alongside node embeddings and edge attributes. Now, the output of the edge model is then used as the input to the coordinate model. to update the position of a particular atom by the weighted sum of all the relative differences with other atoms. Then we have the node model, which takes previous node embeddings and the output of the AG model to update the node embeddings. And then finally, we have a couple of linear layers to obtain the mean and the variance for coordinate embeddings and node embeddings. So we can have multiple EGCL layers, but for this paper, we have seen that using just one of these layers is sufficiently good results. Now, then for the decoder, we have a bunch of densely connected linear layers which produces 3D coordinates and corresponding residue types. Now, moving on to the loss function, what we essentially have here is a sort of variation of a standard loss function of a VAE. So we have this usually reconstruction loss term and KL loss term, but we have also added these three additional loss terms, that is BP loss, short range loss, and long range loss. So as you can see here, we have used 4 different hyperparameters. There is alpha KL, alpha backbone, alpha short range, and alpha long range for controlling the amount of contacts or the amount of effect that particular loss function can have on this total model. Now, for the next part, here comes my co-author Fardina.
Thank you, Tassi. Hello everyone, my name is Fardina. I'm the co-author of this paper, and now I'm going to present the details of how we have actually set up this experimental setup for this project. So our goal here is to analyze the impact of what happens when we add or don't add any predefined constraint in the regular VAE model in terms of model's backbone, short range and long range contact in the generated data that already described by my co-author here. And it effectively is an ablation method because it measures the impact of each terms on the quality of the generated data. So these are our 4 setup actually. So let me go through them. First of all, this is the baseline one, where the value of weight coefficient for backbone short loss and long loss is 0. That means we didn't add there is no additional constant here. This is just a regular VAE loss for the model. Next, we gradually add the backbone constraint only. And in our next setup, we additionally add short range constraint behind also this backbone one. And later, this is the final one for the final experimental setup where we have added all of our 3 predefined constraints. And as you can see, it's like as these parameters are like alpha backbone, alpha short range, and alpha long range. These are all hyperparameter. So we have systematically investigated the impact of the value of this weight, like in a very controlled experimental setting where we have played with different range of values here. And of course, that all the details are not given here. So here I'm going to show you some of our results, and because of the time constraint, we are not going to show all the results, but you can of course check in our paper. So this is the first one, as I said, the first experimental setup, baseline, where is no constant has been added. And if you can see here the table, in the table, the first column represents like what is the percentage of the backbone has been generated over contact map generated by the model. So here just I want to add that for the evaluation, although we have generated 3D coordinates, but for the evaluation purpose, we have actually converted every 3D coordinate generated structures to contact map, and then added this result. So, and the second one is represent the EMD atom over distance between the short range value distribution over the generated and training data set. And finally, in the third column, it represents the EMD distance between the long range value distribution over the generated and training data set. Just want to add that. Here, SRNR is a term we have used here, which measures the number of short range in a contact map, and same like that, LRNR actually measures the number of long range contact in a contact map. So we can see some observations here. First of all, the percentage of backbone is relatively low. So we can say that like the model has not been able to learn any inheritance patterns. And if you can see here in the column 2 and column 2, like for the short range contact, there is very high EMD distance between the distribution over the generated and trained data set. And of course, as it is EMD distance, so we want that the value should be as low as we can, as possible. So next, we show the experimental setup for 2, where we have added the backbone loss constraint only. And if you can see here in the first column, we have actually varied the weight in an incremental manner. And here we have shown some values here, and we can see here that as the value of the alpha backbone hyperparameter grows in the first column, the percentage of backbone is increases compared to the baseline setup. And even we can also see some improvement in the short range contrast, because there is now like lower EMD distance between short range value distribution over the generated and training data set. Then the next one is what happened when we add additional short range constraints in the VAE loss. And of course, we played with the values, and we actually adjust the weight of the alpha short range values in 3 ways, where we have taken in the first one when the value is equal to the value of the weight coefficients of backbone or greater than or less than. And we can see that like adding the short range loss to the VAE loss function actually helps, especially if we can see the value 50. We can see that it is giving the best performance because it is the lowest EMD values for here. And then also we have shown the values for long range contact, and we can see a significant improvement in the percentage of backbone. Although there is some performance degrade for short range contact, but we can see a very good performance for long range because the values has been decreased now compared to before. And here are some visualization of the distribution for now. I'm just showing it for just a long range only, and you can see the mapping of the generated data set blue and the training data set orange, and we can see that whenever we are gradually adding the constraint, there is more overlapping of the distribution of training data set and generated data set. And here is the conclusion here. So we are saying that our model has advanced for computing a multi-structure view, and we can control several aspects of a generated tertiary structure via our proposed novel terms in the loss function. And some of our future work could be like, we want to investigate more variants of equivariant coding based GVAE, and also we want to learn like if we can learn a tertiary structure and sequence of variable length instead of fixed length. And although in this model we have generated both sequence and structure there, but we didn't utilize the sequence yet, but maybe we can utilize it later. Maybe we can make it more general sequence specific structure. So thank you everyone. Thank you for hearing us. So please let us know if you have any questions. Thank you.
So you can take like one question, then we can have second presenter start setting things up. So take one question.
It's interesting to see your conclusion by adding the constraint and long range, short range.
Yes.
The loss function actually affect quite a lot in your generation. We actually noticed related result in the last paper of this session, also about loss functions. So it's interesting. But I have a question in your architecture. I noticed that you have input different kinds of information, but you actually produces 3 models, one called coordinate model, one called edge model, one called node model.
Yeah.
Yes.
How do you, what are they? They're separate models, right? Or?
Yes.
Yes, they are separate models, and they're needed for updating they're basically used for updating the position of the coordinates, right, in the model, so that we can achieve that equivariance. So that's the main thing that we are aiming for here in coding, right? So we are also updating the coordinate embeddings, and we are also updating the node embeddings, so that we finally can obtain some useful mean and variance through which we can decode our 3D tertiary structure.
Maybe I can add a little more, as this is a graph variational autoencoder. So, for every structure, for every protein, we are actually taking as an input as 3D coordinates, and of course, their sequence. So, we are also taking their contact map also. So, if you can see here in the H model, it is as a H, it is actually mapping if there is contact or not, and it is taking the 3D coordinate in the coordinate model, and also the sequence one in the node one. So this is the way we have actually, implemented the architecture. Thank you.
Thank you. Let's pen the speaker one more time.
Yeah, I think we have taken so much time, but thank you. We are here. If you have any questions, just let us know. Thank you, everyone.
Thank you. So we don't have second talk now.